Hello, students. This is Dr. Joa. In this lecture, we're going to learn about reactions of alcohols. So that is, an alcohol is going to be one of our reagents. So here we see a tertiary alcohol reacting with HCl or HBr acid. This could also be a secondary alcohol, and this reaction would still work to give us an alkyl halide. So alcohols, secondary and tertiary, can form alkyl halides using acids. So our nucleophiles are going to react with our HCl or HBr to generate this reactive intermediate. The water is now ready to leave, where the OH was not a good leaving group, forming a carbocation. Because we started with a tertiary alcohol, we formed this tertiary carbocation. If we had started with a secondary alcohol, we would form a secondary carbocation, not as fast, but still forms. The halide that was kicked out, which is, we could just draw it down here, is then going to bind that carbocation and give us the product. The primary carbocations are not stable, so this is not a way to get a primary alkyl halide, but to get a tertiary or a secondary alkyl halide if we use the right alcohol. Now, these reactions are in competition with the elimination, but we will talk about that in just a minute. If we consider a primary alcohol reacting with HBr, it cannot proceed through a SN1 mechanism because a primary carbocation cannot form, but the reaction still occurs. First to know, we're only going to use HBr or sulfuric acid with NaBr, which is going to give us bromide, Br minus, because the bromide is going to be a better nucleophile than chloride. So this is going to be an SN2 mechanism in which the leaving group is again going to be water, okay? But it's not going to leave to form a carbocation like in an SN1. Rather, we're going to have an SN2 reaction in which the nucleophile attacks at the same time as the leaving group leaves. So that allows for the substitution to occur and a primary alkyl halide to form. Now, because this is an SN2, the backside attack is going to lead to inversion of stereochemistry. This is not a chiral molecule, the 1-bromobutane, so it doesn't matter in terms of absolute configuration because it does not apply, but it's good to remember that if we do have 4 groups on the carbon, an inversion would occur. That might matter. All right, so this is a typical SN2 mechanism, but we first have to form our leaving group. Okay, so there are a lot of acids being talked about. So just a bit of a summary here. And just to give you an example, here's a secondary alcohol. Right, so carbon with the hydroxyl is bonded to 2 carbons. That carbon and that carbon. So that secondary HBr works here through an SN1 mechanism. So you can think about that mechanism to give us a very high yield of bromocyclohexane, but there's always that E1 product that we're not showing here. So tertiary and secondary work through SN1. The tertiaries give excellent yield. The primaries react via SN2 with HBr or H2SO4Br minus. Poor yields with chlorides for primary and secondary as well, just because chloride is not such a good nucleophile, or as good of a nucleophile, I should say, as bromide. And our elimination product are always present. So if we were to look at the elimination product here, elimination is the opposite of an addition. So the water leaving group would leave, and then we would form that double bond there. And I'm not just going to gloss over that. We will go into more detail. Okay, so let's look at that mechanism. So now we're considering the dehydration to form alkene. So they're, you know, even if we only focus on the SN1, the E1 is still happening, whether it's just 10% yield or less, they're still in competition. So when we pronate our tertiary alcohols, right, this is a tertiary alcohol, we form a good leaving group. So it's the same thing as we saw in the previous reactions. That leaving group leaves to give us a tertiary carbocation. And now I do have to show some of those hydrogens. I'll show there and there. So we have two types of substituents, an ethyl and two methyls. So if we depronate at the ethyl, we're going to depronate and then form a pi bond. That's going to result in this product, and that's going to be our major product. If we depronate at one of the methyl groups, we're going to form a pi bond here, and then that's going to lead to the minor product. So the tri-substituted product, or the one that's more substituted at the double bond, is going to be major, and then the one that's di-substituted is going to be minor. So how do we determine that degree of substitution? We're just going to look at the carbons that are part of the double bond, and then count the number of carbons that are directly bonded to those two carbons. So this carbon has one carbon bonded to it, and then this carbon has two carbons bonded to it. So that means a total of 3 carbons bonded to the double bond. That makes it tri-substituted. Whereas this double bond here, the carbon at the bottom is di-substituted, so it has 2 other carbons bonded to it. And the one on the top has 0. So we're not counting the other carbon that's part of the double bond. We're saying how many carbons are bonded to this double bond. So the 2 carbons on the double bond are working together to account for that substitution. So we wouldn't count the carbons that are part of that double bond. So this is the E1 mechanism. Zivzet's rule for elimination tells us that the major product is the more substituted double bond. It's more stable. So it's preferred by equilibrium. Okay, so they form equally as fast, but the major product is the one that's more stable. The product is more stable, and so that would be the tri-substituted. They go through the same intermediate, right, the same carbocation, so they form at the same rate. Now, some common acids used for dehydration, they're going to be our strong acids, sulfuric acid, phosphoric acid. And these reactions, they're both done at room temperature and at high temperatures. So it's kind of hard to pin down on which temperature. But heating helps the leaving group leave, which matters more for secondary carbocations than for tertiary because tertiaries form so easily. Okay, so I always think of this, can you get 100% SN1 and E1? So I think it's helpful to, well, I'm really showing this graphic because I had it, but it might be helpful to think back to alkyl halides. So alkyl halides, the leaving group can leave when we heat, carbocation forms, and either a nucleophile substitutes for an SN1 product, or nucleophile depronates for an E1 product. And right there, that's a pretty kind of even distribution. Obviously, there's more SN1 product. You can get SN1 only if there is no beta hydrogen. So if there's no hydrogen that can't be depronated, like to make ethylene or something like that. Well, maybe not ethylene. To make a double bond, if there are no hydrogens available, you just can't have it. And then there's some very specific conditions that have been worked out to just increase the yield of one. So here, just bubbling HCl gas through an ether solution of 1-methylcyclohexanol will give almost uh, completely SN1, right? So substitution, right? But of course, there's still some of this product, okay? And you might even have some of the non-ZZ products, which would be this. So think about how you would generate those two products, right? These would be your E1, the major E1 product being the one on the top. And then these dehydrations, which are very commonly done, are mainly E1, right? So 91%. They're heated, and we might even use like a drying tube just to remove water as it's being uh, kicked off to drive the equilibrium to the right. Okay, so then moving on from tertiary alcohols, how do we make alkyl halides from primary and secondary alcohols without acids? Well, we use these reagents that are electrophiles or Lewis acids, SOCl2 and PBr3. Okay, so SOCl2 looks like this. Whoops. And I think there's another lone pair on the sulfur there, but I didn't count the electrons. And then PBr3 looks like this. So the phosphorus and the sulfur are both bonded to electronegative atoms, so that makes them electrophilic. Okay, and we form these intermediates by the alcohol acting as a nucleophile, right, towards that atom that has the electronegative groups on it. Right, so the sulfur's electron pair there. We can kind of I'm glossing over this mechanism, but essentially we delocalize or we push off two electrons from the double bond up to the oxygen and then back down. And then that's how we kick out the chloride. So why not just kick out the chloride? Because there's some evidence through carbonyls that the charge just get delocalized onto the oxygen first. There is a depronation step that has to happen here, right? Because there's hydrogen on the oxygen. So there are two steps there that are not shown, but I think just being able to show the OH group, the oxygen binding to the sulfur and eliminating or kicking out the chloride is sufficient. Now that chloride is going to participate and act as a nucleophile that's going to bind the carbon, the alpha carbon, and now we have this good leaving group here. Okay. And so then that's going to give us an alkyl halide, and we're going to have inversion of stereochemistry. And so here, let's make this an ethyl, and that way we have four different groups. And you see there's some inversion of stereochemistry. And the reason why is because the SN2 reaction is happening at the carbon, the alpha carbon, the carbon that had the OH group, and now it has the chloride. So similarly, PBr3, although maybe a little bit easier to draw the mechanism because the molecule is a little bit simpler. So the oxygen binds the phosphorus, kicks out the bromide. There is loss of a proton here. Ether is a base that's available, so that can depronate. Although when the reactions balance is shown as the chloride is depronating up here, but ether is most likely the base. That's getting rid of that proton. So if back to PBr3, kick out the bromide, that's going to become the nucleophile. And again, let's make this an ethyl so we show some inversion of stereochemistry there. Because the substitution is happening at the alpha carbon, here's our good leaving group. We're going to end up with inversion. All right. So SOCl2, PBr3 lead to alkyl chlorides or bromide respectively with inversion of stereochemistry. Okay, so maybe that's not what we want. So what do? Will we use a different leaving group rather than thionyl chloride, SOCl2, or PBr3? Oh, wait, no. Let me do an example here. Okay, so there's no stereochemistry shown here. PBr3, very simple example, so it's not. Now let's make this a little bit more interesting. Okay, so PBr3, nothing's happening to this methyl inversion of stereochemistry at this OH. Okay, so what if we didn't want inversion of stereochemistry? What if we wanted that wedge to, oh, there we go. We're making alkyl halides, we're not making alcohols. Okay, so what if we wanted that bromide to be on a wedge, not on a dash? What if we wanted to remain the same with the same stereochemistry? Then we use a tosylate. So we have our alcohol, primary, secondary, reacting with para-toluene sulfonyl chloride, which is or para-toluene sulfonic acid. So at the top here is the sulfonic acid, not sulfonic acid, sulfonic acid, and then the chloride just has a chloride instead of a OH. So this is the tosyl chloride, and this is the toluene sulfonic acid. They will both lead to a tosylate, which looks like this. Okay. And again, we won't show the full mechanism here, just like with SOCl2, but I do want to point out the oxygen is going to be our nucleophile, and then we're going to kick out a leaving group. And this makes a little more sense. It's actually okay to kick out an OH if we form a pi bond. So kick the electrons up, back down, and then kick the chloride out. Okay, so the structure is not shown here completely, but that's going to give us the tosylate. So these are generally called tosylates, which are good leaving groups. So these are good leaving groups. Now we can then, so because the substitution in this step did not occur at the alpha carbon, right? The carbon bearing the OH, there is no inversion at that carbon. So we retain the stereochemistry there. Okay, so we retain the stereochemistry. Now, if we do substitute further with a second reagent, and I'll give you some examples on the next slide, then there would be an inversion there. Okay, so once we have a good leaving group, the nucleophile could be a variety of things. Hydroxides, cyanide, halides, alkoxides, ammonia, and even reducing agents are shown here. This could also be done with alkyl halides, with alkyl chlorides, bromides, and iodine. Okay, although iodides are not used as much. So this is really a list of good nucleophiles for SN2 reactions to make alcohols, nitriles, halides, ethers. And so if our goal was to make an alkyl halide, right, we could just add the halide to the tosylate, okay, and then get that halide. Now let's compare. Oh, PBr3. Yeah, we won't talk about SLCl2, but it'll be the same analogous to PBr3. and then the tosylate. Okay, and let's start with this alcohol. Okay, so that's an R2-octanol. If we treat this with PBr3, an SN2 reaction will occur at the alpha carbon. And so we will invert the stereochemistry. So the hydrogen is forward, and now it's going to be back there. And now this is S. We went from R to S. If we compare this with, oh, my pen is giving out, tosyl chloride, and this does require a base like pyridine is to deprotonate the alcohol. There is a substitution, but it occurs at the tosyl, not at the carbon of the alcohol. And so the stereochemistry is retained. So OTS is now my leaving group. So the hydrogen was forward and it remains forward. So this is R. So if we add a second nucleophile to each one of these reactions to have an SN2 reaction, let's say we add an alkoxide, and then the appropriate solvent. So we'll add the same thing here. So in aprotic polar solvent, we're going to get a second inversion because SN2 occurs with inversion of stereochemistry. So in the top reaction, the hydrogen will be forward again. Okay, so we have inversion. Inversion equals retention. We'll put that in quotations, right? Because we did two inversions, R became S, and then S came back to R. That equals retention. Now for the bottom, we retain the configuration, the R configuration, but now we're going to invert it. And so the hydrogen will end up back where the ethoxide, so I'm just abbreviating the alkyl group there, will end up forward. So now this is going to be S. So overall, this is inversion. So we're comparing the alcohol to this ether that we ended up with, right? And we're going through either our inverted so that we can invert it a second time and retain the stereochemistry, or if we want to end up with inversion, we retain the stereochemistry and in the first step to get the leaving group and then invert. So you might say, why are we doing this? Because our alcohols don't have a good leaving group. These are our secondary alcohols in this case, and also primary. So they don't have a good leaving group, so we convert them into bromides or halides or tosylates, and then react them with a good nucleophile. Okay, so let's move on to oxidation of alcohols, which is the reverse of reductions of aldehydes, ketones, and carboxylic acids. So oxidation is increasing the number of bonds to oxygen. Oxidation is increasing the number of bonds to oxygen. So here we have our primary alcohol with an oxidizing agent. If we use a mild oxidizing agent, which I'll talk about in detail, we're going to get an aldehyde. So here's our alpha carbon. It's bonded to one oxygen. Here's that same carbon. Now it's bonded to two oxygen. It's actually only bonded to one oxygen, but there's two bonds to that oxygen, so we're going to count that as if it's two. So that means that an oxidation happened. We increase the number of bonds to oxygen. If we continue to oxidize with a strong oxidizing agent, we're going to end up with a carboxylic acid, which has 3 bonds to oxygen on that same carbon that we're following there in red to get a carboxylic acid. So a primary alcohol can be oxidized to an aldehyde. Oops. Or it can be further oxidized to a carboxylic acid. As long as there are hydrogen atoms, we can continue to oxidize. Okay, a secondary alcohol only has 1 hydrogen atom, so it can only undergo 1 oxidation. So this carbon has 1 oxygen on it. Using any oxidizing agent, we're going to increase the number of bonds to oxygens to form a ketone. There were no hydrogens on that carbonyl carbon, so that's the end of the oxidation. And so that also means that a tertiary alcohol cannot be oxidized. If there are no hydrogens, there is no oxidation. Okay, because we're actually oxidizing those CH bonds. So here are some oxidizing agents that you may recognize. Potassium permanganate, and then these chromium reagents. Chromium is toxic and carcinogenic. So in practice, we tend to avoid using chromium, and I'll show you some other oxidizing agents. Okay, so I'm not sure what happened to the animation here. So here is a primary alcohol. There are 2 hydrogens on the carbon bearing the OH. So using a strong oxidizing agent, so all of the chromium oxidizing agents except for one named PCC that I'll show you are considered strong, will oxidize all the way to the carboxylic acid. So we don't isolate the aldehyde because this is a strong oxidizing agent. We oxidize 2 times, so we go from 1 bond to oxygen all the way to 3 bonds to oxygen. Okay, let's look at stopping our oxidations. So there are milder oxidizing agents that will allow us to isolate the aldehydes from primary alcohol. So here's a primary alcohol. Here's the carbon bearing the OH. There's only 1 carbon bonded to it. It's one of these CH2 groups. So that's primary. PCC, pyridinium chlorochromate, is one of those mild oxidizing agents, although in practice we don't want to use it because it has chromium. The Swern oxidation is done with dimethyl sulfoxide, coke chloride, which looks like this. That's also an oxidizing agent with triethylamine. The dichloromethane is a base in cold conditions. That's a mild oxidizing agent. And then lastly, this Dis-Martin periodinate, this molecule here, which shows a hypervalent iodine. So iodine, a halide, commonly has 1 bond in 3 lone pairs, so it's monovalent, 1 bond. But here it has 1, 2, 3, 4, 5 bonds to make it hypervalent. It's still neutral, so if we calculate the formal charge there, 7 valence electrons for an iodine, and then 1, 2, 3, 4, 5 bonds, and then 2 lone pair electrons. So it's actually still neutral, but it's hypervalent, and hypervalent iodine is an oxidizing agent, but it's mild. So it will allow us to oxidize just primary alcohols to aldehydes without having to use pyridinium chlorochromate or without having to use the Swern oxidation, which requires low temperatures. Okay, so let's look at the products here. So here's our alpha carbon. That's going to become our carbonyl carbon. Okay, so keep track of the carbons there. Carbon 1 and then 6, 7 carbons, right? So basically, here's your oxygen. We don't look at the mechanisms for oxidations very much, just because they vary so much. So you really want to keep track of the alpha carbon. We're going to oxidize 1 time So we're going to lose a hydrogen and form the carbonyl. So essentially, imagine that you are losing H2. Okay, one hydrogen comes from the oxygen, one hydrogen comes from the carbon. So it's losing H2 across that CO bond. Okay, so here we go, H, H. All right, there's your aldehyde. Now we do use DMP to oxidize secondary alcohols as well. And actually NPCC and DMSO, these can all oxidize secondary alcohols. The point of this slide is that these don't get oxidized to carboxylic acids. But if we were to add a strong oxidizing agent, then we would get the carboxylic acid. That's not really practical doing that, but it is in practice possible. Okay, I'm going to go ahead and skip this example. I do just want to point out PCC is abbreviated, but it is chromium, pyridine, and then HCl, which pronates the pyridine. Okay, so the last oxidizing agent I want to introduce is sodium hypochlorite, which is household bleach. So another alternative to heavy metals. This is a secondary alcohol. So secondary alcohols, because they only have one hydrogen, can only be oxidized one time to a ketone. Okay, so there's our ketone. There's also no acid being used here. So with chromium, there's often acid so this is good if we have like a double bond present, carbon-carbon double bond, and we needed to keep the right, like if there's a double bond there, then acid won't react with it. Okay, so this is, again, you identify a Sworn oxidation, a primary alcohol. So primary alcohols can be oxidized twice, but with Sworn oxidation, so sit up there, we do stop at the aldehyde. So we're only going to oxidize one time, remove H2. Oh, I think that was in the previous slide. So CH2, okay, carbon oxidize one time, just remove an H2 there, and we can isolate that aldehyde. Okay, oh, there's no animation in this slide. So I'm just going to introduce this and then we will come back to it when we talk about ethers. Alcohols and ethers, their chemistry is very intertwined because we use alcohols to make ethers. And actually, I'm just going to rewrite this slide because it's too busy. So to make symmetrical ethers from primary alcohols, we simply use two equivalents of the alcohol and then a strong acid like H2SO4, and we get the symmetrical ether. So this occurs pronation. This is aqueous, so we can just use H3O plus. So we have pronated alcohol. And then we're just going to draw a second equivalent of our alcohol. And this is going to undergo an SN2 reaction. Okay, we cannot undergo an SN1 because it's the form of primary carbocation. No, actually, I don't have to show this. and H3O plus. So the catalyst regenerates. So this is how ether is made, diethyl ether, that we use commonly in the laboratory. We could also make dimethyl ether this way. It really works for unhindered primary alcohols or methanol. Asymmetric and symmetric alcohols, ethers are made through Williamson ether synthesis. So we have an alcohol, usually the bulky alcohol, or one that that does not have an unhindered carbon. Same, that's the same thing. Actually, let me do cyclohexanol here. And NaH. That's the preferred base because it's going to give us a really good equilibrium. So we get a high concentration of our alkoxide. We can put the Na plus just to balance the reaction, although usually I'm going to leave it out. Oh, and then now that we have our alkoxide in high concentration, we add an alkyl halide. And through an SN2, through a substitution, we make our asymmetric ether. Now we have to choose carefully which is the alcohol and which is the alkyl halide, because we need this SN2 to work out well. So we wouldn't be able to use, for example, a phenyliodide, since an SN2 cannot occur there. I mean, we cannot donate there. We wouldn't use terbutyl iodide either for the similar reason. It's too bulky. So we want the halide to be the less hindered, and then the alcohol can be the more hindered. Okay, so we will practice this. There are some examples here, and we will practice this next time we meet.